So maybe you can start. So hello everyone. So today we have the pleasure of listening to Quentin Berger, who's going to talk to us about some results on the Ising model and on Galton-Watson trees.
Okay, well, thank you, Clément, for the invitation. I'm happy to see many familiar faces on Zoom, and I hope to be able to travel soon to South America to meet in person here. Okay, so I'm going to talk about some results I obtained with my PhD student, Irene Ayuso Ventura. She's also doing, she's actually in Paris-Est Créteil with Arnaud. And okay, so I was told that there were students in the room and people from all ages. So I'll talk about some results on the Ising model on trees. So there are some old results by Lyons I will come back to, and some results I didn't know about, more recent on trees, and we'll see the relation with our problem. Okay, so first I'll start with our initial motivation. It was not to study on Galton-Watson trees, but on random graphs. So I will just recall you what the Ising model and what type of random graphs we want to consider. Okay, I didn't say it, but please feel free to interrupt me if you have any question. Okay, so you take the Ising model on a graph. You consider a graph with vertices and edges, and the Ising model on this graph it lives on the state space, which is -1 + 1 to the v. So if you take an element to the state space, it represents a spin configuration, right? So you have spins pointing up, spins pointing down, and you consider this Ising measure. So you put some inverse temperature beta, and you look at this measure, which gives a weight exponential beta times the sum of over neighboring vertices of sigma x times sigma y. Okay, so I guess that everyone in the room knows about the Ising model, and so it favors configurations which have spins that are aligned. And what we can consider is also adding some external field, right? So you put some function h on the vertices, from the vertices to the real numbers. And what you do is inside the Hamiltonian, you have the hx times sigma x. So the spins want to align with the sign of h, and the larger h, the more you want to be aligned with h. Okay, so here I've drawn on these two graphs examples where hx has value 0 or +1. So if you have a 0, you don't feel any influence from the external field. And if you put a +1, you feel as if there's someone with the plus above you trying to align you with plus. Okay, and so if you put this kind of thing, you can think about this external field as being a boundary condition. Okay, and the boundary is just the sites where the external field is not equal to 0. Okay, so that's the Ising model. And what we want to do usually about the Ising model is understand this measure on the large graph. Okay, so you can take the square lattice and look at a big square in the square lattice. You want to understand the role of the external field, and in this talk I will just focus on the magnetization of a vertex x that you take. Okay, so you choose a vertex and you look at the magnetization of that vertex, which is the average value of the spin at the vertex. Okay, if the spins are aligned with the pluses, the magnetization will be positive. Okay, and so you know that there are some phase transition depending on the parameter beta. You have different behavior. Maybe the magnetization will go to 0 or will stay positive if you put some sufficiently positive external field. Okay, so we want to ask that question actually on random graph. Okay, so let me give you the motivation we had. It was to consider the Ising model on the configuration model. Okay, so the configuration model, I don't know if you've came across this model, but it's a classical model of random graph. And it's a random graph where you prescribe degrees of the vertices. Okay, so you start with n vertices, and you give the degrees of each vertex. Okay, so di is the degree of vertex I. And how do you construct that graph? Well, you start with, you draw the vertices everywhere in, okay, you draw the n vertices, and you draw half edges, and you draw di half edges to vertex I. Okay, and then what you want to do is connect half edges at random. Okay, so the first thing you do is you select two half edges uniformly at random among all the possibilities. So you have two, you have dn choose two possibilities. So dm is the total degree of the graph, and you have to assume that it is even. Okay, so you chose two half edges at random and you connect them. Then what you do is there are dn minus two half edges remaining. So you choose two of them at random and you connect them. And then you repeat and you repeat and you have a random graph. Okay? So that's the way to construct a random graph, and there's a whole field of probability which studies the properties, like the connectivity properties of these random graphs. And okay, so what is the question we want to ask on the Ising model with that graph? Okay, so here is a realization of a configuration model with degrees between, I don't remember, between 4 and 6, maybe between 3 and 6, something like that. And okay, so you have the graph and you can put the Ising model on that graph. Okay, and what you want to understand is the magnetization of, well, the magnetization of a given vertex. Okay, so here I didn't put any external field yet. And okay, I talked about boundary conditions. So here you don't have a natural boundary on that graph. And what we were interested in was to put some kind of random boundary. Okay, so you could imagine that there are large M external agents. Okay, so you have agents with a plus, and they want to influence your graph. Okay, so you have small number or large number, and they want to attach to the vertices of your graph. Okay, so you have call them external agents or influencers. If you are on a social network, you want to ask how many influencers you have to put to make people buy some item.
So sorry, Quentin, those are chosen randomly as well? So N is fixed?
Yeah. Okay, so there are two ways of putting them. Either you attach them randomly among the n vertices, or you include them in your construction of the configuration model. Okay, you can say in my configuration model, I have n neutral vertices and m plus vertices, and you connect them this way. Or you can just like construct your configuration model and add some external field. And the way we'll do is, in the simplest way to analyze is just to put a Bernoulli random variable here with probability small. But yeah, M is, you can think about just, you want to add a plus external field to a given number of sites. Okay, and so now what you do is you choose a vertex at random, okay, here in red. You consider the magnetization of that randomly chosen vertex. And what you want to know is how small can you choose big M so that in the limit, as the number of vertices go to infinity, you still have magnetization of that vertex. Okay, so the question is how few external agents you have to put in order to magnetize a randomly chosen vertex. Okay, so magnetize the whole graph. Okay, so you have to take M going to infinity with N, but the question is how fast should it grow with N? Okay, so is the question clear?
Yeah.
Hey, Quentin, is that the question is a quench question or a new question? Do you need
it's an annealed question. It's an annealed question, yes. Okay. It's a good question. So you draw them both at the same time and you answer, okay, so this magnetization will be a random variable and you'll consider it as a random variable both of the random graph and of the boundary condition that we had.
Okay, thank you.
Okay, so that's the question we are currently working on with my PhD student and Remco van der Hofstadt. And okay, so we made some progress, but so the thing with these configuration model graphs is that locally, when you explore the neighborhood of one vertex, it looks like a tree. Okay, so if you start exploring the neighborhood of this vertex, right, you have this neighbor, then this neighbor has a given number of other neighbors, and then this neighbor has another number of neighbors, but you don't see any loops in the vicinity of the initial vertex. Okay, so I don't want to go into the detail of this exploration process, but basically what you can prove is that the configuration model locally looks like a tree. Okay, so that's why we shifted our focus and tried to understand first this same question on a tree, and that's the question I will be presenting today. Okay, so this was just motivation, and now I'll just tell you what the result is. Okay, so take a Galton-Watson tree of depth n, and you assume that the offspring distribution satisfies some assumptions. Okay, so you want it to be supercritical, okay, because in the configuration model you have something, yeah, you want the graph to be connected in the end, so you want something supercritical, so you assume that the average is strictly larger than 1. For technical reasons, we assume that it has finite variance, and also for technical reasons, but not very important, you assume that there is no extinction possible. Okay, so you assume that every vertex has at least one child. Okay, so here I draw a perfectly good Galton-Watson tree, which has distribution concentrated on 2, so direct mass at 2. And okay, so that's our tree, and it was easier for me to draw that tree. And so what you want to do is then you want to add some external field at random. Okay, so you put your external agents on that tree. And this is what I call the sparse external field, and sometimes a sparse Bernoulli external field, because what I'll do is that every vertex I'll attach a plus. Okay, you could think about attaching a positive real random variable, but just the plus makes it simpler, and you can compare these different models. Okay, so the thing is that there are IID Bernoulli with Pareto Pn. So either you put plus, either you don't put a plus. And here on the drawing, I've circled only the ones which are attached to a plus. And the sparse condition means that you want Pn to go to 0. Okay, basically, if Pn does not go to 0, it means that you have a plus at finite distance from the root, and so we'll magnetize the root. Okay, so the quantity you want to study is the magnetization of the root, and you want to know how fast do Pn have to go to 0, or how slow can you take Pn going to 0 and still have the root magnetized.
So, sorry, Quentin, Cédric had a question. He asked if the degree 2 was for convenience here, or if you could...
Yeah, it's just for the drawing. It's just for the drawing because I didn't have enough time to draw nicer pictures. But
Quentin, Can I ask a question? So now you put the random boundary to be plus. If you put it with one half probability to be plus, one half probability to be minus, and how will it change?
Yeah, it's not a question we investigated, and this is one of the next questions we want to study. But yeah, the idea we had in mind was just putting what you can think about that is putting a plus boundary condition on a random geometry.
Okay.
Okay, and yeah, it comes from the idea from the configuration model where you want to add some influencers, and you want to ask how many influencers you have to put, and you assume that all the influencers are pushing in the same direction. But it's true that it makes things more complicated if you put pluses and minuses.
Okay, thank you.
Okay, so yeah, the binary tree is not an issue. It's general offspring distribution, supercritical Galton-Watson tree. Okay, and so what is our result? First, I want to recall some result which is known for the Ising model with the plus boundary condition. When you put pluses only on the leaves, okay, so you take this tree and you put pluses everywhere on the leaves, and the question is, what is the critical parameter for the Ising model for the root to be magnetized? And so the critical parameter is defined by the relation, the mean of the Galton-Watson tree times the hyperbolic tangent of beta equals 1. Okay, if this hyperbolic tangent of beta is larger than 1 strictly, then the root remains magnetized in the limit, and if it's smaller or equal than 1, then it is 0 in the limit. Okay, so I planned on spending some time to explain a bit how this result works, because it's actually the main idea in our proofs, and we have to make several technical adaptations and have some new ideas, but the core idea comes from there. And so what you see is that if you're in the second case, if you're in the subcritical case, already adding a lot of pluses on the leaves is not enough to magnetize the root. And so the idea is that if you want to magnetize the root, you will need this condition to be supercritical for the Ising model with plus boundary condition. Okay, so
sorry, Quentin.
Yeah.
Where are you putting the boundary conditions? You said on the leaves?
On the leaves, yes.
So all the leaves in the Galton-Watson tree. So now it's really a random tree, you say, right?
Yeah, it's a random tree. Okay, so this is a very specific realization of a random tree. And all the leaves, you put a plus on top.
But that means you assume that your supercritical tree is finite, or?
No, it's an infinite tree, and you consider only up to depth n.
Oh, so you cut it off. I see. Okay.
Yeah, you cut it off. You cut it off, and you let n go to infinity.
So all the vertices at height n are in particular trees, and then there are some more.
Yeah, exactly.
Leaves, right? Okay, thank you.
Yeah, thank you.
And Pn does not play any role here, because you said Pn goes to 0, right?
Yeah. Okay. So here it's this first part is a reminder for what happens if you don't have Pn. So you put boundary conditions on the leaves. Okay. Here. Thanks. Here it's with plus boundary condition. What happens? Well, just to recall you or tell you if you didn't know, it's a very nice result. First by Russell Lyons, and our result was to say what happens when you put random boundary conditions. Okay, you put random external field, sparse one, okay, with the parameter Pn, and we find essentially a necessary and sufficient condition. We say that, okay, put yourself in that case. So if you put pluses on the leaves, you will magnetize the root. But if you put pluses on all the leaves, it means that your parameter Pn is not going to 0. And the question is, how many pluses can you remove and still have the root magnetized? Okay, and the answer is the following. If Pn times this parameter to the n remains positive in the limit, then the root remains magnetized, and if it goes to 0, then the root, the magnetization of the root goes to 0. Okay, so it means that you can take Pn going to 0 exponentially fast, but with an exponential decay rate which cannot be too fast. Right? Is the result clear?
Sorry, but here you assume that the degree is bounded by below, no?
Yeah, I assume that that the degree is at least 1.
Yes, but I mean, so here on the graph it is on the drawing it is 2.
Yeah, on the drawing it is 2, but it could be 1.
It could be maybe 1, at least 1. Okay, but
yeah.
Okay.
Yeah, maybe my drawings are maybe it was a bad idea to draw binary tree, but Okay, so
Hey, Quentin, sorry. Is it
Yeah.
possible to use your result to imply the result by Lyons?
yeah, actually it's the same method. Actually, it's a more recent method by Pimentel and Paris, but I'll come back to that. I'll explain to you the method, and you'll see how things work.
Okay, thank you.
Okay, so this is the result I want to tell you about a bit about the techniques of the proof. Okay, and
Quentin?
yeah.
Yes. So in principle, you could play around also with the parameter beta here.
Yeah.
So if beta depends on n.
Yeah, this thing works as too. Yeah.
Okay.
Yeah, let me think. Yeah, no, that works as well.
Okay. Thank you.
Yeah. Okay, I have to think about it, but I'm pretty sure it works. Okay, so before I go on to the proofs, and first I'll go into the proof of the first part with plus boundary condition. Let me go back to the configuration model. Okay, so if you go back on the configuration model, the total number of vertices will be roughly m to the power n, right? You have a tree with the mean offspring distribution m. After small n steps, you have roughly m to the n people in that tree, vertices in that tree. And the number of external agent will roughly be pm times n. Okay, so Pn is the probability if you're having a plus attached, and so you have a proportion Pn of the large n vertices which have a plus. Okay, and if I just write this condition in terms of m and n, this gives me that this condition is m times n to the power minus some alpha, denoted alpha critical, and this is the alpha critical. Okay, it's just a simple calculation. Okay, and so what is our prediction is, okay, so here you have to make some approximations, and I don't think we hope to get a result as precise as the one we obtained here for the tree, but basically what we expect, and I think we will be able to prove, is that if the number of agent is smaller than n to this critical exponent minus epsilon, so it's the randomly chosen vertex will not be magnetized, and if the number of external agent is larger than n to the alpha critical plus epsilon, the randomly chosen vertex will be magnetized in the limit. Okay, so we identified the exponent. Okay, we want m to grow polynomially in the total number of vertices, and we identify how this exponent should be. Okay, so that was initially that was our heuristic, and I think we are close to being able to prove that. Okay, so that's our result, and okay, I'll try to give you an idea on how we prove this result, but first I need to introduce the tools that are used to prove this thing. Okay, so now I'll go on the Ising model on a tree, on a Galton-Watson tree with plus boundary condition, and when I say plus boundary condition, I mean on the leaves. Okay, and there are two things. First, a result by Lyons, which identifies the critical point, and then I will talk about the critical case. Okay, so here's the result by Lyons. Okay, so it's the setting we were in. So you take an infinite tree with some root, and you denote Tn, the restriction of the tree to the first n generations. Okay, you put plus boundary condition on the leaves of that tree. And the question is, when does the root remain magnetized in the limits? And you see that condition appear. Okay, so it's hyperbolic tangent of beta times what is called the branching number of a tree. And if that quantity is strictly smaller than 1, then the root will not be magnetized. And if this quantity is strictly larger than 1, then the root will be magnetized. Okay, so the branching number of a tree, it's, okay, so here I didn't make any assumption. It was a deterministic tree, right? It was a deterministic tree. And you can define what is called the branching number of that tree, which roughly describes how fast the tree grows. Okay, and for Galton-Watson trees, this branching number is equal to the mean, I should say almost surely. Okay, so here you identify the critical point, and the critical point is the inverse of the tangent hyperbolic of 1 over n. Okay, m is the mean Austrian distribution. Okay, so how do you prove that? It's by now it's a very classical result by Lyons by the end of the 80s. And so what was the idea of Lyons is that since you're on a tree, you're able to actually get some recursion on the tree. Okay, and the idea of Lyons is to, instead of looking at the magnetization, looking at some other quantity that satisfies some recursion. Okay, so what it considers is what he calls the log likelihood ratio. So you look at the log of the probability that the root is +1 divided by the probability that the root is -1. Okay, and you can see you have a relation between this log likelihood ratio and the magnetization of the root, just as a simple transformation. Okay, and in particular, this magnetization will go to 0 if and only if the log likelihood ratio goes to 0. Okay, and once you've done that, what you can see is that you have a recursion on the tree. Okay, and so what is the recursion? So here I put some details of the recursion. So what you have to do is, okay, take a vertex u in the tree and look at this log likelihood ratio inside the subtree rooted at u. Okay, so I don't know if it's clear. What you do is you have a big tree, choose a vertex u, and look at all the descendants of u inside the tree Tn. Okay, so you have a tree of height, which is n minus the height of u. And you look inside that tree, the Ising model, and there the u is your new root, and you can look at the log likelihood ratio in this tree. Okay. And then after some calculation, which is not really complicated, what you find is that you have some iteration. Right? The log likelihood ratio at a vertex u is the sum over its children of a function of the log likelihood ratio of the children of v. Okay, and I've put it in that form for convenience later. Okay, and here this function is explicit, and it's 1 over hyperbolic tangent of beta, inverse of tangent hyperbolic beta, tangent hyperbolic beta, tangent hyperbolic x. Okay, so it looks complicated, but it's not that complicated, and it comes from the specific Hamiltonian of the Ising model. Okay, and I've put here the tangent beta away outside because I want the f beta to be normalized. Okay, so let me draw what f beta looks like. So you have this recursion, and the f beta here, it's concave, and its derivative at 0 is 1. Okay, so I've normalized it so that the derivative at 0 is 1. Okay, and here you see that you have a hyperbolic tangent of beta up here, and you have a sum over the children of u, and so if you take the average, you'll see the m hyperbolic tangent of beta up here. Okay. So that's the way Lyons solved this problem, and there's one bound which is fairly easy.
Sorry, Quentin, it is on the right hand side. It is r and beta plus v, not r and beta plus u.
Oh yeah, it's true. Yeah, here it's a v. You're right. Thank you.
Okay.
Okay, so yeah, the log likelihood ratio at the vertex U is a sum of its children of a function of the log likelihood ratio of the children. Okay, and here what you see is that you have a very easy upper bound, right? You can bound, since f is concave and bounded by x, you just iterate the inequality f beta x smaller than x, and what you obtain is that you have hyperbolic tangent of beta to the n. Okay, you start from the root and you go up. You have hyperbolic tangent of beta to the n. Okay, you've iterated n times, and you have a sum over the leaves of the log likelihood ratio of v. Okay, but if you remember what I told you is that what is the definition of this? It's the log likelihood ratio inside the subtree rooted at v. And so if v is a leaf, there's no subtree rooted at v, and so you can bound this by a constant. Okay, I've put beta here, but okay, you can just think about the constant, and so you just have the number of leaves in the tree. Okay, so you have that the log likelihood ratio of the root on the left is bounded by this term to the power n times zn, and zn is the number of the total number of leaves, the total number of children of a Galton-Watson process. Okay, and here you see that what you want to do is normalize this zn by m to the n to obtain the usual martingale associated with Galton-Watson trees. And what you get is that the log likelihood ratio of the root is bounded by, you see this m hyperbolic tangent of beta to the n, and it goes to 0 if this is smaller than 1 and not 0. Right? So we've proved one part of Lyons theorem. Okay. So one observation with the Lyons result is that here I didn't tell you what happens at the critical point. And it was actually not treated in Lyons' results because this one already identifies the critical point. But what happens at the critical point was dealt with later by Pimentel and Perez. And to be able to talk about that case, I need to introduce some things I didn't know about 2 years ago. It's nonlinear resistive networks. So first, I will recall you how networks with resistances work and tell you how you adapt that to have nonlinear resistive network and how it's related to the Ising model. Okay, so if you're not familiar with resistive networks, it's okay. It's just, I'll give you the definition. So what you do is you have a graph equipped with resistances on the edges. You have some vertex A and some subset Z of the vertices. I don't know why I put some edges here. And so you want to define the effective resistance between this vertex A and the set Z. Okay, so how you do that? You define a flow between A to Z. I'll put the definition of a flow there. So flow is something that's defined on the edges, and the flow across an edges crossed in reverse is minus the flow of the edge. And you have that at each vertex, the incoming flow is equal to the outgoing flow. Okay, and you can define its energy. Okay, so you have the resistance at edge E, and you take the flow square. And so the effective resistance and conductance between A and Z is, okay, the resistance is the infimum of the energy of a flow over, and where the infimum is taken over all unit flows. Okay, unit means that the outgoing flow from A is of some 1, is positive with some 1. Okay, and the conductance, the effective conductance is the inverse of the resistance. Okay, and you know, with these definitions, you have the rules that if you put two resistances in series, the resistance is the sum of the resistances, and if you put two resistances in parallel, the conductance is the sum of the two conductances. Okay, and what we could do is actually replace these two by some other parameter P. And that's what is called the P resistance and P conductance. Okay, so what you do is define the LP energy of the flow with P strictly larger than 1, put the power R to the P minus 1 and the flow to the power P. And you define the P resistance and the P conductance similarly. Right, and actually a lot of things that you know on resistive networks, they also work on nonlinear resistive networks. And the only thing that changes is that it's when you consider the rule for the resistances in series or in parallel, they change, right? And okay, here there's another parameter which is convenient to write is P minus 1, call it S. So instead of having that the resistances of if you put two resistances in series, it's not the sum of the two resistances, but you have this power S that you have to put there. Okay, and you see that if if P equals 2, you recover the rules that you know, meaning that S is equal to 1. Okay, so that's maybe a heavy definition, and if you're not familiar with the resistive network, it might be coming out of nowhere. But if you are familiar with resistive networks, it's not much of a difference from the from resistive networks. And so why is this related to the Ising model on the tree? Because of the following. Okay, so this is actually an observation made by Pimentel and Paris in 2010. So you have the rules to compute conductances of resistive networks. And so what you can do is consider on a tree of depth n, you can consider the effective conductance between a vertex u and the boundary. Okay, so these are the leaves, right? And so you have your set A, which is a vertex of your tree, and you're looking at the resistive network, which is the subtree above U. Okay, and you want to compute the effective conductances between this vertex U and the boundary of the tree, meaning the leaves. Okay, and if you multiply that by the resistance of the edge leading at U, what you have is this recursion. Okay, so it very much looks like the recursion we had on Ising.
So we have a question from Cedric in the chat. I don't know if you can see it by yourself.
Yeah, nonlinear is because P is not equal to 2. When P equals 2, here you have a linear relation between the resistance in series and the resistances of the individual resistances, and same for conductances. Here, the relation is nonlinear.
Okay. Thank you. Sorry.
No, it was an important question. Okay, and so what you see is that you have a rule, an iteration on the tree for the conductances, for the P conductances. And what you have is that you have a function. Okay, so let me tell you again, as for the Ising model. So the conductancy, the P conductance between a vertex U and the leaves is the sum over the children of U of a function of the P conductance between the children of U and the leaves. Okay, and this function is explicit. It's this one. It's x over 1 plus x to the s to the power 1 over s. Okay, I recall you s is P minus 1. Okay, so for P equals 2, it's still nonlinear. It's x over 1 plus x. Okay, and so this looks like a lot to the Ising model, and Pimentel and Paris, they showed the following, is that if you look at the log likelihood ratio, you can compare that with the P conductance between the root and the leaves. And the P that you should choose here is P equal 3. Okay, I'll explain just in a minute why P equal 3 here. And what I have to tell you is that the conductance of a resistive network, it comes with resistances, right? So you have to equip your tree with resistances on the edges. And so here what you have to put is the resistances hyperbolic tangent of beta to the power minus u, okay, minus the depth of u in your tree. Okay, because okay, here you see that if you choose your resistances like that, what you'll see in this ratio Ru divided by Rv is exactly hyperbolic tangent of beta. Okay, so they have a relation, and once you have this relation between the log latitude ratio or the magnetization of the root and the P conductance of the tree, then you have all the tools from resistive networks to help you trying to estimate this P conductance. Okay, and in particular, this answers the question of the critical case. In the critical case, you have beta critical here, you replace beta by beta critical. This hyperbolic tangent of beta is 1/m. And so it's related to whether the P capacity of the infinite tree is 0 or not. If you look at the resistance, it's the P resistance is infinite or not. Okay, so let me go to yp equal 3. Yeah.
Here, the resistance Ru, it means between you and its children?
Yeah, between you and its ancestor. Yeah, sorry, I went too fast on that. So here it's true that I indexed the resistance by a vertex, and this is a convenient way to talk about the resistance below u, right? So it's between you and its mother or its father.
Okay.
Okay, and okay, so yp equal 3, well, it's just related to this function, right? Hyperbolic tangent of beta. Okay, so what you have is that your function gp here, it also has the same property that it is concave, and it's bounded, and it has derivative 1 at 0. And so what you have to look at is what is the behavior near 0, right? So what is the how fast is your function approaching the line x when x goes to 0? And it turns out that if you do the calculation, f approaches x as x cubed, g approaches x as xp. So if you want to compare this function f of beta for the Ising model and this function of p for the P conductance, you have to take P equal 3. And that's actually what they do there. They just say that you can compare the F beta x and the G beta GPX, and then you basically iterate and you get this relation. Okay, so they did that, and we were quite surprised that actually they didn't compute the P capacity of a Galton-Watson tree. Okay, so they talk about spherically symmetric trees or things like that, but they don't compute P capacity for Galton-Watson tree. So it's something that we did with my student. We said for Galton-Watson tree with the offspring distribution Z, the P conductance at the critical point. So the Ising critical point is when you choose the resistances to be m to the power minus u. Right, there should be a minus sign. Okay, so I changed. Okay, so the signs are incorrect, but it's not that important. And so we are able to estimate quite precisely the P capacity of a Galton-Watson tree. Okay, and we show that it decays like n to the power minus 1 over P minus 1 if the Galton-Watson tree has a finite P moment, and otherwise it decays slower.
Sorry, can you repeat what maybe you did say it, but what is the P capacity exactly? How would you define it?
Yeah, okay, so yeah, that's an important part. So the P capacity is defined here. So maybe let me focus on the P resistance. Okay, so the P capacity is when I say P capacity, I mean P conductance. Because for me, it's more natural to talk about P conductance because it's a resistive network, but Pimentel and Perez, they talk about P capacity. So,
it is not related to the capacity in potential theory, or it is? Yes.
It is.
It is, yes, okay.
Yeah. It is, yeah. But yeah, the way to present it, I think it's with resistive networks, it makes more sense to me, at least. Okay, so the P conductance of Galton-Watson tree at the critical point decays like n to the -1 over P minus 1. Okay, so for instance, for the Ising model, if you have a third moment for the offspring distribution, then you have a decay like n to the -1/2. And apparently this was not known in the literature. I don't know, it was strange to me, but okay. So we are just finishing this paper. And it's not that difficult to get this part. Okay, do you have other questions on this part? Okay, good. So now I will come back to our original model, which is the Ising model with the sparse external field, and tell you how can we adapt these tools to deal with that case. Okay, so let me recall you what the original problem was. So you put a sparse external field on a Galton-Watson tree, so Bernoulli random variable with parameter Pn going to 0. Okay, so I've put some Bernoulli random variables inside my whole tree. And okay, so what I told you before is that in Lyons iteration, it's really easy to get an upper bound, and the lower bound is harder, and it's actually where maybe you need the P conductance. But actually here, it's also the same. You can get an upper bound. You can make Lyons iteration work and get an upper bound fairly easily. So I will not get into the upper bound. I will get into the lower bound. Okay, and if I want a lower bound on the magnetization of the root, what I can do is just remove some of the pluses, right? So what I'll do is I'll remove the pluses that are not on the leaves. Anyway, they are mostly more or less the same proportion of pluses on the leaves and inside the tree. So I remove the ones that are inside the trees. And so what you have here is a problem which is analogous to the one before. So you want to put plus boundary condition, but not everywhere on the leaves, but on IID Bernoulli variables on the leaves. Okay, so what you'll do is actually you will reduce to the case of a tree with plus boundary condition to be able to use Pimentel-Perez argument, right? The comparison between the log latitude ratio of the root and the P conductance, you don't use at all the fact that it's a Galton-Watson tree. It's true on any tree. Okay, so what you can do here is that you can reduce your tree to keep only the branches that lead to pluses, and you'll get a lower bound. You'll get actually an equality in that case. Okay, so here's the way to reduce your tree. We call that pruning the tree by Bernoulli process on the leaves. Okay, so you put IID Bernoulli random variable on the trees. You consider all the branches that lead to a +1, and you remove all the other branches. And that gives you a subtree of your initial tree, your Galton-Watson tree, which I'll denote Tn star. And this is what we call the pruned tree, right? And now what you have is you have the Ising model on a subtree, but with plus boundary condition. And that's where you will be able to use the P conductance. Okay, so then you'll have to compute the P conductance of that tree. Okay, so our first work was to study that prune tree. Okay, so this is just what I said before. The magnetization of your initial model of the root is bounded from below by the 3 capacity of this modified tree. Okay, so it turns out that this prune tree, this modified tree, is actually a branching process. Okay, but the thing is that it has some inhomogeneous offspring distribution. Right? It's not obvious from the construction, because the way you construct it is you start from the leaves, you construct a subtree from the leaves, and you remove some branches up. So it's some kind of top-down up construction. But you can show it's an inhomogeneous branching process. Okay, and here you take the law that you take is the joint law of the tree and the Bernoulli process. Okay, and you have some explicit distribution for this offspring distribution. Right, so roughly this offspring distribution is you take a number of offspring Z and you cut some of them and you keep some of them with probability gamma k. Okay, and this gamma k is a parameter of the model. Okay, so it's basically what you do is you grow your branching process, and at each vertex you will remove a certain number of leaves. And this offspring distribution is conditioned on being larger than 1. Okay, so why is it larger than 1? Because if you are inside your tree Tn star, it means that you are coming from a leaf at the top which has a +1. So you need to have at least one children going up in that direction. Okay, and this probability gamma k here in the binomial is roughly the probability that an individual at generation k is not pruned. Okay, so we have fairly explicit expression of it. And you can study that expression. Okay. So that's I know that that's a lot to take in, but key fact is that the way you pruned your tree from the leaves, you prune a lot of branches. What you obtain is a Galton-Watson, is a branching process, but inhomogeneous. And the idea is that when you are at the bottom of your tree, this parameter gamma k will be close to 1, right? It's very likely that one of your child is connected to a plus eventually. But the further and further you go up, this probability goes to 0, and in the end, it will be concentrated on 0. So this distribution will be concentrated on the direct mass at 1. Okay, so here is a proposition which tells you exactly that. There is actually a phase transition in this tree. Okay, so there is some critical parameter which depends on n and on Pn, right? If you think about Pn decaying exponentially, tells you that this k star n is of order n, right? Let's say it's 1/2 of n. And what you have is that if k is much smaller than k star, meaning that it's this k star minus something very big, then this probability is close to 1. Okay, and when this probability is close to 1, it means that your offspring distribution is close to the original offspring distribution. And on the other hand, if k is much larger than k star, meaning that it's k star plus something very large, this gamma k is going to 0. And if gamma k is going to 0, it means that this binomial wants to be equal to 0, but it's conditioned to be larger than 1. So this offspring distribution is concentrated on a direct mass at 1. Okay, and here what I want to point out is that this phase transition is very sharp. It happens at K star plus something of order 1. Okay, if it's K star minus something very big, this gamma K is 1. If it's K star plus something very big, this gamma K is 0. Okay, so let me show you some picture. Okay, so here is a prune, here's a tree, Galton-Watson tree. So here is properly random. So here's the root. And what I do is I put some Bernoulli random variables on the leaves and I prune them. Okay, and this is what you obtain. So here what you see is that what happens at the core of your tree will not move, right? You won't prune anything inside your tree. And what happened on the outside of the tree near the leaves, you will actually delete a lot of branches. Okay, so here you see that what you have is you have some K star. Below the K star, you look like your original Galton-Watson tree, and after this K star, you look like very thin branches with minimal. Okay, so sometimes you have some branching, but it's very unlikely. Okay, and this is actually all we need to be able to compute the P conductance of such a tree. Okay, so maybe I'm done with the time. I'll tell you just the first part of the thing. So what we need to do is we need to control the 3 conductance of this modified tree. And what you do is you just use the fact that this 3 conductance is bounded from below by the usual resistance to the -1. So you need an upper bound on the resistance from the root, on the resistance of this modified tree. Okay, and I will call you the definition of the resistance. It's the infimum of a quantity. So what you have to do to get an upper bound is just to choose wisely the unit flow that you put there. Okay, and just put some uniform unit flow. And okay, I'll just skip the details because I think I'm done with the time. And you do some calculations, and you see this Pn m hyperbolic tangent beta to the n appear. Okay, so what we managed to do is control the resistance of this, the effective resistance between the root and the leaves in this particular modified tree, and show that it's bounded if and only if this quantity does not go to 0.
So Quentin, so in the end, what does it mean for the scaling of K star?
Oh, for the scaling of K star, yeah. So the scaling of K star is this one. Okay, so
yes, okay, n minus. Sorry, I missed it. Yeah.
Yeah.
So n minus. Okay. Thanks.
So the K star is okay. If you think about Pn as being I don't know, lambda to the n, so decaying exponentially fast, your K star will be a constant times n, and you have a sharp phase transition at that constant times n.
Yeah. Okay.
And the key is that you don't want that constant times n to be very small, because otherwise you have only thin branches.
Yeah. Yeah, that makes sense.
Okay. And so I'll stop there. Thank you.
Okay, so thank you very much, Quentin. So there have been a number of questions during the talk, but are there other questions? So Cedric has a question, I think.
Yes, thank you very much. So I would like to know if you have some different distribution of the external field. Can you do something, or because here it was just barely, but you could imagine something different, or is it possible, or to extend?
Yeah. So the thing is that if you take any positive random variable or a random variable which is 0 with a given probability, and then positive with the probability Pn, you can do all the same thing, right? The fact that it's really a plus is not important. If you can bound that by epsilon, you're fine. You'll just get some constant that depend on the lower bound you have. You can have some comparison between the the processes, and you can always compare random variable with Bernoulli, with a constant times the Bernoulli.
Mm-hmm.
Okay, so yeah, the idea is that if you can lower bound your random variable by a constant time of Bernoulli, then you are in business. And for the upper bound, since the upper bound is usually easier, I think you can do it by hand and find the same type of control.
Mm-hmm. Okay, thanks.
Any other question?
Yes. So I have a so this gives you this last slide gives you the control over the P conductance. So then I imagine that if K star is proportional to n, then what you modify the critical beta by a constant factor, or?
Yeah, exactly. The critical beta is the one such that this starts going to zero or starts remaining going to plus infinity, right? If you think about Pn as being lambda to the n, if you go to the theorem, I'll just go to okay, remember where the theorem is. Yeah, that's here. Okay, so if you go to that theorem, if you put Pn to be lambda to the n, here you have your new critical point, your new critical beta. So in practice, yes, your Pn is changing the critical beta.
Okay, so if like if you're percolating like well, okay, if the set of if your magnetic field acts on a like a positive fraction of the boundary on a logarithmic level, then you still have a phase transition, right?
Yes.
Does something similar happens on ZD, or is it specific to the tree? Like if on ZD you take a.
Okay, I'm not sure. I don't know. It's a good question, but I would say that if you, okay, so if you put, yeah, I don't know, but I would guess that the same type of thing happened, but I'm not sure where you have to put the threshold for changing the critical temperature.
Okay, thank you. And by tuning P like around this like not being exactly a power, can you change what happened at criticality, or?
It's a good question, and yeah, you can change. For instance, if you take Pn equal to lambda to the n, what you'll see is that at criticality, this quantity is strictly positive. So it means that at criticality, you are magnetized. And so it's not the same behavior as the original one where you put only plus boundary condition.
Okay. Thank you.
So yeah, what we have is actually, it's a good control of the P conductance. And so the P conductance is roughly the magnetization. So we have a control of the magnetization, and the P conductance, if I put the last slide, you have this bound, right? And this m to the k star is actually Pn m to the n. Okay, so we have, yeah, I think we have a good control.
Any other question? Cedric again.
Yeah, sorry. I have a question about what is the assumption of the Galton-Watson tree that you consider? It is the do you assume some moment condition of the offsprings?
We assume, yeah, we assume a second moment condition.
Okay, and so in this case, what would happen if you have some not second moment condition?
Okay, so the thing is that here you have some kind of monotonicity between the p conductances, right? The smaller p is, the smaller the p conductances. Okay, so in principle, you could say, I'll just compare it with some conductance with the p very close to 1. And here what you have to replace these two by p minus 1. So what, by p, sorry. So what you have to do is control some, instead of controlling second moment, you'll have to control p minus 1 moments and p moments. And so it's only just a bit more technical, but I think our result should hold as well.
But the results will not be modified. They will be exactly the same.
No. It would not be modified, but it would change, right? It would change. So what we have now is that this quantity, okay, so what the question is this resistance remaining bounded? And here we have a necessary and sufficient condition if the resistance, for the resistance to remain bounded, is that this quantity does not go to 0. Okay, because it's 1, it's there. But if you put a parameter p here, what you have it will be roughly, I guess, this quantity to some power. So it will not change the condition that if this goes to 0, then you blow up, and if this does not go to 0, then you don't blow up. It will change the way in which you blow up. Is that, I don't know if that was clear.
But you can do it. Yes, but so you can do it in this case.
Yeah, in practice we can do it. Maybe I can go to the case to this result, right? So if you want to compute the P capacity of a Galton-Watson tree, you have two different behavior. Okay, so this is at criticality, but you have two different behavior depending on whether your Galton-Watson tree has a moment of order P or not. If it has a moment of order P, this P capacity will be n to the minus 1 over P minus 1. So 1/2 in the Ising model. And if you have a heavy tail with parameter alpha between 1 and P, you have to replace this P minus 1 by alpha minus 1.
Okay,
so it still goes to 0, but not at the same speed.
Okay.
And in our main theorem, I was just interested in knowing whether this goes to 0 or not.
Okay, makes sense. Okay, thank you.
Any other question? Okay, so if there are no other questions, let us thank Quentin again for a very nice talk.